In the 1940s, early forms of telecommunication, such as telephones and radios, relied on devices called valves, or vacuum tubes. Valves were devices used to amplify electrical signals. However, they were expensive, needed a lot of power, and broke easily. They were also quite large, which made the equipment they were part of quite chunky. ENIAC, the world's first electronic computer, was built in 1947. It was about the size of a small house and contained a staggering 17,468 valves or vacuum tubes. There was an urgent need to find a replacement for valves, which happened in 1948, when the first transistor was invented. Transistors were small, cheap, reliable, and used a minimal amount of power. They quickly replaced valves in many types of electric circuits. But their success led to further problems as they became used in ever more complex circuits. Increasing numbers of transistors and resistors had to be soldered into circuits. In 1959, the first integrated circuit, or IC, was made, in which a whole circuit was cut into a single piece of silicon. This led to the possibility of mass production and the founding of Silicon Valley, which today is home to many of the world's largest technology companies.
Ignition sequence start.
During the 1960s, the space race between the United States and Russia drove the development of small-scale electronics operating in rockets and satellites. ICs, or chips as they became known, quickly became smaller and more complex. Significant improvements in design and manufacturing processes have resulted in chips of ever-increasing complexity, sophistication, and miniaturization. By the start of the 21st century, the chips used in powerful computers were delivering processing speeds that allowed filmmakers to create whole stories using computer-generated imagery, or CGI. These days, people known as teardown experts make a living from identifying the design chips and components in the latest electronic devices as soon as they're released into the market. These silicon chips have led to the revolution in electronics and the vast number of electronic devices that enhance our daily lives. We can begin to understand the science behind electronics by studying the materials they are made of. Materials can be classified into conductors, insulators, and semiconductors in terms of their electrical conductivity. Conductors are usually metals. In a material that conducts, the outer electrons are not bound to a particular atom. They move freely within the material. If a voltage from a power source is applied across a conductor, the negatively charged electrons are free to move towards the positive terminal of the power source. According to band structure theory, there are two bands in materials: the valence band, where the outermost electrons in the atom are, and the conduction band, where electrons can go. In conductors, the bottom of the conduction band of possible energy levels for electrons overlaps the top of the valence band. This means that there is no energy gap. So there are always plenty of electrons in the conduction band, ready to carry an electric current when a voltage is applied across the conductor. In insulators, all outer or valence electrons are closely bound to atoms. Glass is an insulator, and its major component is silica, or silicon dioxide. It forms a crystal structure of silicon, and oxygen atoms sharing electrons in covalent bonds. There are no free electrons. If a voltage is applied across an insulator, there are no free electrons available to carry a current. Band structure theory asserts there is a large energy gap between the top of the valence energy band and the bottom of the conduction energy band. To cross this gap, an electron needs to gain a large amount of energy, such as a very high voltage being applied. In normal circumstances, there is not enough energy available to allow electrons to cross the gap, so there is no flow of electrons and no current. Silica, or silicon dioxide, is an insulator, but the elements silicon and germanium are examples of semiconductors. On the periodic table, semiconductors are elements that have properties in between conductors and insulators. Semiconductor atoms with 4 valency electrons each form covalent bonds with 4 neighbours, so that each atom sees 8 electrons in its outer shell. In terms of band structure theory, there is a gap between the valence band of electron energies and the conduction band. But this gap is smaller than for insulators. So a small amount of energy can sometimes make an electron free to move. For example, if the material is heated, some electrons gain sufficient energy to move into the conduction band and carry a current when a voltage is applied. Many modern electronic devices, such as solar cells, light-emitting diodes, and integrated circuits, or ICs, contain semiconductor materials. So how can a material that doesn't really want to conduct electricity well be made to conduct? Doping, or adding small amounts of other substances, can boost the conductivity of a semiconductor. There are 2 types of doped semiconductor material, P and N type. Remember that silicon or germanium atoms with 4 outer electrons each bond to each other by sharing their outer electrons, so that they see 8 electrons in their outer shell. N-type material is made by adding a small amount of an element that has 5 electrons in its outer shell, such as arsenic or phosphorus. But when arsenic is added, there is a spare electron from each arsenic-silicon bond. These spare electrons are available as conduction electrons. The material is called N-type because the majority charge carriers are negatively charged electrons. P-type material is made by adding a small amount of an element that has 3 electrons in its outer shell, such as aluminium or gallium. Where aluminium infiltrates the silicon lattice, there's a missing electron or net positive charge, referred to as a hole. The material is called P-type because the majority charge carriers are positively charged holes. When a voltage is applied across the material, holes move by electrons from neighbouring atoms moving into existing holes and leaving behind new holes. As this process is repeated, the holes effectively move one way, as electrons move the other way, from atom to atom. To summarise, in both N-type and P-type materials, we add a small amount of another material to the silicon. This creates a semiconductor with a boosted conductivity and an improved ability to conduct electrons. Diodes are used in many modern electronic devices. A diode allows current to flow in one direction, but not the other. Diodes are always connected in series with a resistor, called a limiting resistor, that increases the circuit resistance and protects the diode from large voltages or currents, which could damage it. A diode is made when a section of p-type material with positive holes as majority charge carriers is placed in contact with n-type material, where the majority charge carriers are negatively charged electrons. Where the two types meet is called the p-n junction. At this junction, some electrons from the n-type material diffuse across the junction into the p-type material and fill holes. At the same time, some holes from the p-type material diffuse into the n-type material and are filled with electrons. As the electrons move from the n-type into the p-type material, the arriving electrons negatively charge part of the p-type material. At the same time, part of the n-type material becomes positively charged as the electrons leave. The result is a region around the junction called the depletion layer, where there are very few mobile electrons or holes. It's as if the electrons have been playing musical chairs, and in the depletion layer, all the electron players have found shares. This is the circuit symbol for a diode. A diode is made from a piece of p-type material joined to a piece of n-type material. The wide end of the triangle is called the anode and is the p-type section of the diode. The other end is called the cathode and is the n-type section. If the p side is connected to the positive terminal of a battery and the n side to the negative terminal, something interesting happens. The positive holes are attracted to the negative terminal and the negative electrons are attracted to the positive terminal. The depletion layer shrinks and current flows through the diode. We say that the diode is forward biased. When the battery terminals are reversed, with the negative terminal connected to the p side of the diode and positive terminal to the n side, almost no current flows. We say that the diode is reverse biased. This graph shows how the current flowing through a diode changes as the voltage across the diode changes. Here, when the battery is connected the other way so that a small reverse voltage is applied, only a minute current flows, called the leakage current. When a large reverse voltage is applied, a large current flows and the diode breaks down. In this region, although the voltage is now positive, the current is still very small. The diode is not really conducting. The point at which the diode starts to conduct is called the threshold voltage. For most silicon diodes, this is about 0.6 to 0.7 volts. The threshold voltage is the voltage needed to reduce the depletion layer enough so that current will flow. Once the threshold voltage is reached, the voltage drop across the diode stays the same, regardless of how much current flows through it. There are many different types of diodes, such as light-emitting diodes and photodiodes. LEDs, or light-emitting diodes, emit visible light. In all diodes, whenever a conduction electron combines with a hole in the p-type material, a packet or photon of electromagnetic energy is released. In silicon-based diodes, the energy is in the infrared range of the electromagnetic spectrum. Diodes made from certain different materials release photons in the visible light range of the spectrum. For example, LEDs based on gallium arsenide emit red light. Green LEDs are made from gallium phosphide. LEDs are used in traffic lights, bike lights, power indicator lights, digital clocks, and many other applications. Remote control units use infrared LEDs as transmitters. LEDs are light-emitting diodes used to produce light. Photodiodes work in the opposite way to LEDs in that they detect light. If a diode surface is exposed to light, the photons provide enough energy for electrons in the conduction band of the p-type material to move across the junction. Similarly, holes in the valence band of the n-type material move across the junction to the p side. This means that by shining light on a photodiode, you can produce an electric current. If the photodiode is not biased, that is, it is not connected to a power source, then a voltage builds up inside the diode, leading to a current flowing. This is the photovoltaic effect, which occurs in solar cells. Normally, a diode that is reverse biased does not allow a current to flow. But if a photodiode is exposed to light when it is reverse biased, a photocurrent will flow. This means that the diode is off until a light shines on it. When it switches on, photodiodes are used as receivers in remote control units, in CD and DVD readers, security systems, and many other applications. Transistors are semiconductor devices widely used as amplifiers and switches. A transistor is a sandwich in which the bread is one type of semiconductor material and the filling is the opposite type. The middle is called the base, sandwiched between the emitter and the collector. In an NPN transistor, the emitter and collector are N-type and the base is a P-type semiconductor. When the transistor is on, the emitter-base junction is forward biased and the base collector junction is reverse biased. Free electrons in the N-type emitter move away from the negatively charged emitter plate into the P-type base, where some recombine with holes, producing a small base current. Most electrons cross the base into the more positive collector, resulting in a much larger current between the emitter and collector. Positive holes travel from the base to the emitter. A small signal in the base emitter circuit causes a much larger, amplified signal to flow from emitter to collector. In this circuit, a small base current here produces a large, amplified current here. By far the most common type of transistor used today is the MOSFET, or metal oxide semiconductor field effect transistor. MOSFETs are core components in the integrated circuits that control our computers, cars, phones, and all other electronic devices. An N-channel MOSFET consists of a layer of P-type semiconductor with two regions of highly doped N-type material connected to terminals called the source and drain. A third metal terminal forms the base. The semiconductor layer is capped with a layer of oxide that insulates it from a central metal terminal known as the gate. When a voltage is applied so that the gate is positive, electrons in the p-type material are attracted towards the gate, forming an electron channel between the source and drain. A strong current flows and the transistor is on. If the gate becomes negative, electrons are repelled and the channel is cut off, preventing a current from flowing between the source and drain. The transistor is off. So changes in the gate voltage switch the transistor on or off. In modern electronics, MOSFETs are microscopic, with the distance between source and drain being no more than a few nanometers, or millionths of a millimeter.